Hello everyone. In this video we're actually going to be doing one of my favorite problems, and it's a simple problem, but there's some intuition to it that actually led me astray when I first did it, and it was very difficult for me at the time. But when I understood what was happening with the aid of my professor, he did a wonderful job of explaining it to me and gave me that solid intuition to go forward and understand the question and solve it. So I'm hoping that I can give you that kind of alleviation if you have done it before and you haven't had any clarity. If you've never seen this before, I hope that when you do see it, you can apply the same line of thought to it and arrive at the same conclusion that I did. So right now we have a ball player because Bobby J is on vacation, so we're just using a generic ball player. A ball player catches a ball 3 seconds after throwing it vertically upwards. What velocity did he throw it with, and how far did it travel? Okay, so immediately we know that we're dealing with things in the vertical axis. Okay, so we know that our displacement is in the vertical axis, and we know that our velocity is in the vertical axis. However, we only know two things about the situation. We only know that gravity is negative 9.8 meters per second, and we also, well, I'll take out the negative because I've accounted for the negative inside those equations. And we only know the time that the ball is out of his hands in the air, and the time that it takes for the ball to leave his hand and come back to his hand is 3 seconds. So other than that, we're pretty much in the dark here. However, let's see if we can draw the situation. So this is the return point, okay? This isn't, maybe I can extend his hand further upwards. My marker is running out. Okay, generic ball player, today I'm going to give you green hands. So the ball travels upward. It travels vertically upward. Okay, so this is the ball here. Okay, so I'm going to call this journey 1. I'm going to name this 1. This is the ball's first journey. Okay, now over here I'm going to draw a separate diagram, and this is the ball coming back down. Okay, I'm trying my best to denote these so you understand what's happening. Okay, this is journey 2. Now, we know that it takes the ball 3 seconds to leave this point and come back to this point. Now, in the time that the ball leaves that ball player's hand and he catches it again, we can assume that nothing happens to this ball, and we're neglecting air resistance. So we can assume that this ball goes vertically upwards, and we can assume that this ball comes down vertically. Now, I'm going to draw a graph. If I were to plot this motion as a function of time, and if I were to plot displacement versus time, and the ball has some displacement, I'll call that, well, let's start it right here. Let's start it right here at the origin. The ball travels here, and the ball returns to its same displacement. And we'll notice something about this motion. It's parabolic. However, there's something else about this motion. The motion is symmetric. When I say symmetric, it's symmetric about this line, because this ball is traveling upwards, and in order for this ball to come down, it has to change directions because it's traveling upwards with some velocity, a positive velocity, and as it goes higher and higher and higher, as it slows down, its velocity is becoming less positive, or smaller and smaller, and then it hits 0 when it stops moving, because at this point now the ball is changing direction. So now when the ball is coming down, it starts to speed up. However, the velocity is now negative because of our coordinate axis. Okay, so because this motion is symmetric, and it takes 3 seconds to go up and come back down to the same point, we can assume that it takes an equal amount of time to go up, and it also takes an equal amount of time to come down. Because if it did not return to the same point, let's just say this is our 0 point right here. If it didn't return to the same point, your graph would look something like that. Or if it went lower, your graph would look something like that. And we could see from here that this is not a symmetric graph. So that is the intuition, that the motion is symmetric. It returns to the exact same point from where it was launched from. And that right there, that helps us a lot, because we know that it takes an equal amount of time to reach that point where the velocity stops, which is also the maximum height. And it takes an equal amount of time to come all the way back down. So I know that T1 plus T2, which is the time to go up or journey 1, or the time for journey 2, which is come down, this is equal to T, which is equal to 3 seconds. However, T1 is equal to T2, because again, it takes an equal amount of time to go up as it does to come down. It's not like there's anything interfering with it, and it comes back to the exact same point from which it was thrown. So this must mean that I have 2t, or 2t1, or 2t2, it doesn't matter, is equal to 3. So t1 is equal to 1.5, which is also equal to t2. Now we know a whole lot more than we did last time. So we actually have the time that it takes for this object to reach its maximum height, and the time it takes for this object to return from that maximum height coming back down. And honestly, it's not something that I would have figured out on my own, even though there are some texts that they explain the symmetry. And this is actually a really convenient tool. It simplifies a lot of problems. So we know that the time it takes to reach its maximum height is 1.5 seconds, and they're asking us, what velocity did he throw the ball with? Well, we know something when the object reaches its maximum height. When the object reaches its maximum height, if you have anything in your hand right now, preferably something that isn't sharp or dangerous, I just want you to throw it up, okay? And look at the highest point that that object goes to, okay? And just for a moment, for an instant, that object is not moving. Because in order for that object to come back down, its velocity has to change directions. So the velocity must be 0 at that highest point. So we also know at the highest point, the final velocity in the y is 0. So we know here Vy is equal to 0. Now I'm going to go to this new section, and I'm going to write this header. Or actually, I'll just put journey 1. So for journey 1, the initial velocity is still a mystery. However, we do know the time is 1.5 seconds. We know gravity is 9.81 meters per second squared. And we also know that the final velocity for this journey is 0, because during journey 1, it starts with an initial velocity. This is him throwing it up, and at the end of journey 1 is right here when it reaches its maximum height. Okay, so at its maximum height, we are convinced that the velocity is 0. We're concerned with that instant. So we have initial velocity, we have final velocity, we have gravity, and we have time. So we can use the first equation, which says this right here. And simply substituting things in, we get 0 is equal to v naught in the y minus, put brackets there, 9.81 times 1.5. So v naught y is equal to 9.81 times 1.5. I'm working this out. This is 9.81 times 1.5, which is 14.715 meters per second. Now, is this consistent with our coordinate axis? Yes, because the object is going up. So this velocity is positive. This means the object is going up. Now, what happens when it goes down? Well, the question didn't ask us what happens when it goes down, but it did ask us to find something else. It asked us to find the maximum height. Now, we can also find the maximum height because we can look at the object's change in displacement. This could be the ball here. This will be y naught. And up here, this will be y. This is the highest the ball goes, and this is our change in displacement. So they want to know, how far does the ball travel in 1.5 seconds? And we know, we may not even need to draw this, because we know that the distance traveled in 1.5 seconds is, in fact, the maximum height of the object. Okay? That is given. So we can also go and we can use this equation. The change in displacement is equal to the initial velocity in the y times the time minus 1/2 gt squared. So filling this out, I get 14, I'm going to round that, 14.72 times 1.5 minus 1/2, 9.81 times 1.5 squared. So working this out, we get 14.72 times 1.5 minus 1/2 times 9.81 times 1.5 squared. And our final answer is 11.04 meters. And this is the maximum height that the ball traveled. And we can go over a few things straight from the beginning. We know that the motion is symmetric. It returns to the exact same point from which it was launched from, the ball. And it took 3 seconds to go all the way up and come all the way back down. So it must have taken it 1.5 seconds to get to the top, or its maximum height, and 1.5 seconds to come back down. And we know that when it's at its maximum height, its velocity there, the instant it reaches that maximum height, is 0. And that enabled us to find its initial velocity, the velocity that it was initially thrown with. And from that, we were able to find the height. We were able to find the height after it travels for 1.5 seconds. And we know the distance traveled after 1.5 seconds is equal to its maximum height. Now, it takes a while, and doing a few of these, this is going to become more natural for you. And if you're here doing this, thank you so much for taking the time to listen to this and to hopefully practice this, or to even try this on your own. And that's what I'm striving for, to help foster independence amongst yourself. So give yourselves a pat on the back, a round of applause, go buy some ice cream, and if you're lactose intolerant, something that your stomach can tolerate, but you deserve it. So I can't wait to see you guys again. So until next time.